Thank you very much. Thank you for the invitation to be here. I'm always happy to be in Paris. And the next speaker told me that I made a mistake giving the first talk in the morning, and I'm still happy that some of you made it in the cold morning of Paris to this talk. So thank you for waking up early in the morning. If I would have given this talk 5 years ago, I would probably have focused yet again on how to treat surfaces as manifolds, as metric manifolds, and how to try to compare between manifolds when trying to compare between shapes. So comparing between shapes, matching shapes, classifying shapes is what I'm trying to do in my research. And we believed, and we still do believe, that treating surfaces, manifolds in nature, as a geometric structure, as metric manifolds is what we should do. Especially axiomatically, I mean defining the invariants of a specific group of transformations, and then extracting from these invariants the operations that we would like to do on the surfaces. And what I would like to present today is some way of migrating this line of thought into networks. I mean, this is where my students are taking me, so I surrender and I go along the flow. But so that we still don't forget where we came from. I mean, axiomatic would still be our infrastructure in a sense. Before we do, let me just remind myself at least, what is the difference between a manifold and a Riemannian manifold. So a manifold is a topological quantity, if you like. Using topology, for example, the manifold at the top, the mag, is topologically equivalent to the manifold at the bottom, to the donut, and a topological sphere is a topological sphere. Things are becoming a little bit more interesting when we are attaching a metric to the manifold. So when we say how we measure distances on the manifold, it becomes a little bit more interesting, because then we can measure the discrepancy between manifolds beyond the topological issue. I mean, we can say that these two manifolds here are, in a sense, almost isometric. I mean, you can measure the discrepancy between them, for example, using the Gromov-Hausdorff distance. The question is, how can we use this idea in order to define signatures for surfaces? And for that goal, let me go through the following. This would be the most technical part of the talk, and this is just to warm up. And afterwards, you will mainly see pictures, so bear with me for the next, I would say, 5–10 minutes. So think of the following idea. I have a manifold M, and I'm attaching a metric to this manifold G. So G, in a sense, is the afferent transformation that takes the coordinate system onto how we measure distances on the surface. And then I attach a different metric to the same manifold. Let's call it G tilde. So I have two manifolds, and I know the exact correspondence of one manifold to the other. I mean, I know exactly how manifold is related to the other one, because I have point-to-point correspondence between these two manifolds. Now, if I have a metric on the manifold, I can define the Laplace-Beltrami operator. And the Laplace-Beltrami operator can be diagonalized. I mean, I can extract the eigenfunctions and corresponding eigenvalues of this Laplace-Beltrami operator. I can do it for this first metric, and I can do it for the second metric. And then the claim is that something that was invented, I would say, 6 years ago or 7 years ago, which is called functional maps, the dot product, the inner product between these two set of eigenfunctions, between these two eigenspaces, is a signature of the manifold. Now, this is a claim that needs to be proven. I will just give intuition of what is going on behind it when choosing very specific metrics. But this is the concept of what I will try to convey. And in fact, using this kind of self-functional map, this dot product between the eigenbases, is what would serve us in order also to train a network to do classification of shapes. So again, what we would like to do is compute the G and the G tilde to, assign two different distances to the same manifold, and then then do the dot product, the inner product of the corresponding eigenfunctions. And the claim would be that the resulting matrix would be a signature of the shape. Okay? And then what we basically do is translate the problem of comparing between smooth manifold into that of comparing between matrices. we take a geometric problem, and like Descartes, we translate it into an algebraic one, which is supposed to be more simple to analyze. So, okay, this was the technical part. This was the envelope. This was the structure of what we will try to do here. But before that, let me just give some motivation of where we are extracting our data. I mean, what is two-dimensional manifolds? What are we talking about? So when I came to the Technion many, many years ago, I had a grant by which I could either hire 3 PhD students or buy a 3D sensor. Now, computer vision at the time was about segmentation, and I said, if this is where all the crowds are walking, we should go into a different direction and somehow extract the geometry of the world by some other means. For example, humans are extracting 3D by 2 different projections of the world into a left eye and a right eye, and then the brain, by solving the correspondence, is extracting the geometric structure of the world. Buying an instrument like that can do stereo was very expensive at the time. It would cost me as much as 2 PhD students. So I gave 1 PhD student an assignment to build such a system. This is how it looked like. This is a stereo system. You have, you can think of 2 eyes, but replace one of the eyes with a projector, and you have an easier 3D sensing device. What we did at the end of the day is packed it and sold it to Intel through a company that is called Envision. In Intel, they took this kind of device and minimized it. I mean, we helped them. They took the projector and squeezed it into 3.2 millimeter. This is Muli Eden, the Israeli VP of Intel Israel at the time, presenting it in CES. So the projector became a 3.2 millimeter width device. This is how it would look like. So what you can see here is basically the projector, a camera, and an RGB camera, and then brain on the right. And it was sold by, it was sold really nicely, and Intel was quite happy with that. But when you're taking a device like that with high power and effective optics, and you squeeze it into 3.2 millimeter, you lose a lot. You lose a lot of accuracy, you lose a lot of quality that we are used to. I mean, when we design, as researchers, a device like that, we take care of accuracy and of efficiency and time, but then when the industry is coming into play, what they are optimizing for is basically the cost of the device, and when the cost of the device goes down, the quality goes down as well. So we have a device that gives geometry in a very rough manner, and the question is how to reconstruct it. Now again, when I was a graduate student, I was confronted with a problem which is called shapeform shading. This is taking an image and extracting the 3D geometric structure from this image. And it was such a beautiful problem. It was solving an iconal equation, and it was so beautiful that I thought that no one would ever use it for any practical usage. And recent advances showed me that I was really wrong. And let me show you how you can use it using this kind of sensor that I'm talking about. So with the sensor, you get a really lousy or really noisy impression of the geometry. And you also have the image. So you have some rough estimation and the image. And what you need to do is just use the Lambertian law so that the dot product between the light source direction and the normal of the surface is equal to the intensity that you're getting in order to enhance the image. So what you see here at the top is what the sensor is providing. And what you see at the bottom is how we use this kind of equation, the iconal equation, or sort of iconal equation, in order to enhance the image. So you can see that you can see much more details at the bottom compared to what you see at the top. This runs on Intel RealSense in real time. And you can actually see, if you compare the two heads, that you can see that, in a sense, we say that this is a denoised image. So I told you that there is a way to extract, to acquire geometric structures from nature. Do it by stereo, do it by time of flight, use whatever means that you have. And then the question is, how do we compare between them? How do we put a glove on a hand? How do we say that this is a hand rather than a leg? And for that, let me go back to philosophy that was actually initiated here in France, as well as some other places. And this is the idea of using differential geometry or geometry at large in order to analyze shapes. So what you do is you look at the objects in the image, for example, and you're asking what are the transformations that are happening to these structures. So if I'm looking at the hand here and here, I mean, if I'm looking at these two projections, then probably there is some affine transformation that is relating between the appearance of the hand on the right eye and the appearance of the hand on the left eye. So I should devise methods that would be invariant with respect to this kind of transformations. So which kinds of transformations are we interested in? For example, the Euclidean transformation is rotation and translation of this shark in the plane. If I shear and squeeze one of the axes as well as rotate and translate, then I'm getting the affine transformation. And if I restrict my transformation to have to preserve area or volume, then what we are talking is what is known as the special or equi-affine transformations. So these are really simple transformations that in image processing we used to care about. I mean, we still do. And the question is, how do I use the idea that there is a known group of transformations that I need to deal with in order to compare between two shapes? So I can look at the contour of the shark, and I can plot a function of the, for example, in the Euclidean case, the x-axis would be the Euclidean arc length, the regular Euclidean axis. The y-axis would indicate the second invariant, which in the Euclidean case is the 1 over the radius of the osculating circle at each and every point. This is what is known as the curvature, the magnitude of the acceleration. And if I plot the graph along the boundaries of these two planar shapes, what I would get is a way of aligning these two shapes. Okay, so this is the red one, and this is the yellow one, and they should align. But we still don't know where to start. In a moment, we'll get rid of this ambiguity. And the first question that comes in mind, can we take this classical way from differential geometry and train a network to come up with graphs like that? So this is an assignment that I gave one of my students, Gautam Pai. And there is not a big problem here. I mean, you can synthesize as many shapes as you like, planar shapes, sample them differently, and rotate and translate them in the plane, and then feed it, for example, into a Siamese network, and thereby, first of all, extract the arc length with some trick. I mean, it needs to be a triple network. And if you use a Siamese network, then you can extract the curvature. And what you get is something which is very similar to the curvature graph. So traveling along the contour, the red one would be the curvature computed numerically, and the blue one would be the output of such a network that approximates the curvature. So we can learn curvature. And from the curvature as a function of arc length, we can reconstruct back the shape up to rotations and translations. The question is, can we get rid of this initial point? And the answer is yes. In fact, there is a theorem by Cartan that tells us that if I'm taking the curvature and the derivative of the curvature with respect to the arc length, then what I'm getting is a signature which is for which we don't need to know where the initial point here. I mean, putting the red shark over the yellow boundary shark, I can use both of them. Okay, so this is one way. So remember, curvature as function of arc length somehow provides information about the shape, up to translations and rotations. And with more complicated groups, we also resort to the invariant arc length, and then the second invariant, plot them one as a function of the other, and then we can compare between shapes. Can we do it for surfaces? Before we go to surfaces, let me introduce, by the way, just to tell you, if I'm running along this curve with the Euclidean arc length, and I'm looking for the eigenfunctions of the Laplacian of traveling along a curve, along a closed contour, then what I would get is the Fourier. Okay, so the Fourier would be the outcome of this of the second derivative operator. Okay, and this is quite trivial. It would be the natural way of representing smooth functions on the manifold. Now let us resort to a different group of transformations, a very specific one that I really like. And this is the one that is similarity or scale invariant. So I have two curves, and I would like to measure distances along these curves. And the arc length that would be invariant to such distances would be, for example, the change of orientation of the velocity vector. Okay, so the change of orientation of the velocity vector would take us from the beginning of the curve to the curvy part over there, and it would correspond to the same distance over there. So the change of angle would be a scale invariant arc length. But by definition, it is also equal to the curvature, to 1 over the radius of the osculating circle, times the Euclidean arc length. Now think of the following conceptual idea, and if you get this, then you would get the rest of the talk, more or less. If I'm traveling along a curve, and I'm parametrizing myself with an arc length like that, and I'm looking at the Fourier, the composition of the second derivative with respect to this arc length, I'm getting a Fourier sequence which is modulated by the curvature. Now, if I hit this Fourier basis by the regular Fourier basis, I can somehow encode the curvature function along my curve. Okay? So there is a way of taking the decomposition of these two arc lengths, the regular one and the scale invariant one, hitting them one with respect to the other, and thereby extracting the curvature. And if I have the curvature as a function of arc length, then I probably can get back the surface itself. Okay, so this is the concept that I would like to convey here. Now, let's lift all this idea to surfaces. In surfaces, there is the regular metric, and there is more than a single curvature. For example, there is the beautiful Gaussian curvature. And Gauss was so profoundly pleased with the curvature, with the multiplication, with the modulation of the two principal curvatures, because they were invariant to how you embed the surface in 3D space or in any dimension. And if you integrate over this quantity, then you can get a topology of the surface. It was a beautiful extension of the curvature to surfaces. Now, if you take the regular metric that is written over here, okay, so you have some parametric surface, S of u and v, and this is how the regular metric looks like. And now you multiply it with the Gaussian curvature, what you would get is a scale invariant metric. Okay, so taking the curvature, multiplying it with the Gaussian curvature would yield the scale invariant metric. And now you can actually see where I'm heading. I have the regular metric, and I have the scale invariant one. The scale invariant one, in fact, encodes the Gaussian curvature as described on the surface. Hitting the eigendecomposition of the corresponding Laplace-Beltrami operators would give me some representation invariant to embedding of the surface. So again, this is how the Laplace-Beltrami operator looks like. And if I would replace it with the invariant version, then this is how it would look like. So this is Laplace and this is Beltrami, and this is Gauss and Riemann. So you can in fact get this kind of metric and use it in order to somehow encode the structure of the surface. Now let me just give you some better motivation of how the eigenfunctions look like, and I would plot the eigenfunctions as colors on the surface itself. So if I'm using the regular metric, and this is an armadillo where one of the hands are stretched and the other one is squeezed, and these are the first eigenfunctions plotted on the armadillos, and you can see that at the top and at the bottom, you get different kinds of eigenfunctions using the regular metric. If I would use the scale invariant one, then the eigenfunctions would obviously correspond. But this is beyond the discussion here. In a moment, I will give you more motivation of what are the equivalent classes with respect to the scale invariant and the regular one. And what you need to take home for that is that these two matrices capture different quantities of the surface. The first one is the regular one. The other one, I mean Fourier in general. The other one captures the Gaussian curvature on the surface. Now we'll try to take the philosophy of Descartes. And this is basically translating geometric problems into algebraic one. And it would also allow us to go into the domain of learning, because in deep learning, one of the tools that everybody is using and exploiting up to its last bit is the fact that we have convolution. We have this shift invariant transform, and it allows us to do convolution, and it allows us to duplicate our structures in the domain of the image. And in geometry, we don't have it. I mean, in geometry, we have some problems. So let me just jump over the fact that now everybody is going into this direction of Jan LeCun and Joe Hinton, and this is the deep neural network, and the infrastructure is having a convolution property. And the question is, how can we have a convolution property, or what can we do with geometries that would allow us to use this kind of machinery? For that, I will try to give you some motivation of a tool which is called functional maps. And this is a powerful, really powerful method, especially in the sense of the ability of providing academic positions. The authors of this paper, so Max Ostianikov has a position here at the Ecole Polytechnique, Justin Solomon in MIT, Mirella Benchen at the Technion, and there are others. What are functional maps? Assume that you have two parametric domains. One of them is S and the other one is P, representing the same function, but there is some stretching and squeezing of the function of translating it from S to P. Okay? So again, these are the same values, or they're in the same order, but there is some squeezing and stretching of the parameterization S and P. Now, assume that I have, and somebody is actually giving me this transformation between S and P. Now, this somebody also gives me some orthogonal basis on S and another different orthogonal basis on P, and allowing me to represent my function by projecting it onto these orthogonal basis on P and on S. And the claim is that the relation between the coefficients of representing F on S and representing F on P, so here it would be beta, and here it would, sorry, alpha, and here it would be betas, is a matrix C. And it doesn't really matter which function you're using. I mean, as long as the stretching and the squeezing of S with respect to P is the same, it's the same T transformation, then the same, it's quite easy to see that the same matrix would also apply to the coefficients of projecting my function on P and projecting my functions on S. Okay? Now, this is a trivial idea, one page and you can prove that. The question is, how can you use it in order to compare between shapes? So now S and P would no longer be one line of squeezing and stretching, but rather two shapes. So this is my domain now. So I have a horse domain and a dog domain. And the question is, how can I compare between them? And now the transformation T is unknown. The idea is to use features in order to solve for these C functions. So if I have enough corresponding features and I truncate my matrix C to be, for example, 5 by 5, 25 numbers, and I have enough features, useful features, for example, if I have a body detector or a nose detector or a leg detector, and I have 25 of those, I can solve, I have enough constraints in order to solve for C. So this is the idea behind functional maps. Having enough corresponding features would allow me to define a least squares problem that would solve for C. And the question is, how can I use the concept that I've shown you a couple of slides ago in order to somehow come up with a signature for the horse or for the dog? Can I do that? And the answer is tricky, but very simple if you got the idea of functional maps. What we do is, instead of using two shapes, we use a single shape. But instead of using one metric for the horse and corresponding metric for the dog, what we'll do is use two different matrices. One, for example, the regular one, and the other one, the scale invariant one. And now the C function, since we know the correspondence, the T is known. The T is the identity. Each point remains at the same position. The only thing that changes is the eigenfunctions of the corresponding Laplace-Beltrami operator that I'm now taking the inner products of these two eigenspaces. So taking the dot product of these two eigenspaces would give me indeed an invariant signature, and thereby translating the problem of matching between smooth objects, geometric objects, into comparing between two matrices. And this is something that a network can actually deal with. I have a universal parameterization and everybody's happy. And this is how it would look like if I'm applying this idea for horses and for this lady here at the bottom. So what you see from the left, top left to the right, and from the top left to the bottom is the eigenfunctions in an increasing order. So you order them from low frequency to high frequencies. And the colors that you see are actually the values of the dot product between, first of all, the first eigenfunction, et cetera, et cetera. So in a sense, I'm encoding the Gaussian curvature in this kind of matrix, and then I can actually compare these matrices and come up with classification of shapes. Now, this is not as simple as it looks. I've put all the dirt under the rug because, for example, when you are decomposing the when you're decomposing the Laplace-Beltrami operator, you have a sign ambiguity. You may have similar eigenvalues that would span subspaces, and then you need to really take care of what is going on in these subspaces. But these are things that you can deal with. I mean, dealing with such problems is something which is relatively easy compared to the original problem. So let me go a little bit further into the idea of what are the eigenfunctions that I'm using. So what you see here at the top is this person. And at the top, you see the leading eigenfunctions of the regular Laplace-Beltrami operator. And at the bottom, you can see the eigenfunctions of the scale invariant version. Okay? So you can see that after 1, 2, 3, 4, 5, at the 6th or 7th eigenfunction, you can see that the high frequencies are actually concentrated at places with high curvature, high Gaussian curvature. These are the fingers of this object. And why? Because if you multiply the area, I mean, if you multiply the arc length by the Gaussian curvature, then it would inflate, in a sense, all these regions with high curvature. And the regions with flat curvature, I mean, the flat regions would basically shrink into points. Let me emphasize that point by looking at, it's called a spherocylinder or whatever. I mean, combination of a sphere and a cylinder. So take a sphere, bisect it in the equator, lift it up, and glue it with a cylinder. Now, if the cylinder is really, really, really small, I mean, goes to almost 0, then from a Euclidean point of view, there would be no difference between this, or epsilon difference between the sphere and its glued version. But from the scale invariant one, the cylinder has a 0 Gaussian curvature. So all these points, in a sense, would shrink into a singular point. So all these surfaces would be equivalent, isometrically equivalent, from the point of view of the scale invariant metric, but they would obviously be different from the point of view of the regular metric. So what we do is we take the eigenfunctions with respect to the regular, the eigenfunctions with respect to the scale invariant, we hit them one with respect to the other, and now what we do is we measure the discrepancy between the C matrix of each and every surface. We pile that, we collect it into a huge matrix, and we, for example, embed it into this space. And if we do it for example, this is the Shrek 2010, 3 objects from there. You can see that each point here corresponds to a different pose of a dog. Each red one, each green one, person, and each blue one, a horse. And you can see that classification is done in a fairly simple manner. If we do it for more challenging examples, this is, for example, the Shrek 2014, and this is the discrepancy. Color here corresponds to the value of distances between these matrices. So, and each row and column here correspond to a different pose of the object at the top. So this baby here and this person over there. So you can see that now if you take these surfaces and you are bending in 3D space, you can see that it is very easy to do clustering, to distinguish between the different characters here. And then if we take it to more challenging examples, this is the Faust from Germany, from Michael Blake's group. Then you can see that, again, you can still do classification in a very straightforward manner. And now the question that comes in mind is, can we actually use this functional map idea? And in fact, I will go back into something which is more crucial. Into the intergeodesic distances that characterize a shape, which is what we were promoting about 5 years ago. And this is the idea of comparing between two shapes by measuring for the shape x all the distances between point xi and xj, and somehow comparing it. I mean, take this as a matrix. So we have this matrix I or j, and then comparing it by permuting. So this would be a permutation or a mapping of another matrix y. And here you have y. I mean, you have all the entries of yi and yj. Obviously, this should be different. Coordinates. So we somehow try to minimize this kind of a measure by solving for the permutation. Okay, we call this the generalized multidimensional scaling problem. If you can compute it exactly, then in fact you're approximating the Gromov-Hausdorff distance between these two surfaces defined as metric spaces. And if you do it in the spectral domain, then we called it spectral GMDS. So this is an idea that we try to promote at the time. And now I will show you how we can take it into a network. So let me start with the results. And this is a joint project, recent one, with my students of Halimi, Orly Tani, Manuel Rodola from Roma, Alex Bronstein. And it would be presented in CVPR 2019. I mean, my student told me that it was accepted, and now it's online, and we'll also put the code online, so it would be a joy. So I have a reference shape, and I would like to somehow match each and every point to different kind of shapes. And the question is how to do that. And the idea is quite simple, assuming you got the hang of functional maps. So if I have computed this C function, okay, the C matrix, then what I can do, apparently, is multiply it on one hand with the eigenfunctions that correspond to the X shape, at the other end with the eigenfunctions that correspond to the left shape. And if I have enough eigenfunctions, then the result would be the permutation, okay? So if I have been able to compute this C, the way of translating between basises, then I have been able to somehow compute the permutation. However, it is very difficult to compute the C, and if I'm truncating this basis, I will no longer have a permutation, but rather some smooth way of transition between a point X on the X shape and some probability of where the X is existing on the Y shape. And what we have been doing is training for this C function. Now, this specific paper is a correction on a previous one, which is called Functional Map Net by Orly Tani and his colleagues. And what they did over there, and I would just give you a nugget of how we corrected, how we revisited what they did. What they did is they used a supervised measure of finding the discrepancy between two surfaces, and for that, they needed to have the point-to-point correspondent between point S and point Q, or surface X and surface Y. What we did is we wanted to get rid of that requirement. And for that, we defined a new measure which basically tries to fit the intergeodesics between surface S and surface Q. So in a sense, it would be a network that solves for the spectral GMDS. Why? Because it works in the spectral domain. So it's a network that would compute this C function, this functional map metric, using the measure that I'm showing here in the spectral domain. Now, if you do that, apparently what we have been able to achieve are results that are in par, almost the same as the supervised version. In fact, you can refine it afterwards by invoking a method which is called product space refinement, but it doesn't really matter. What I'm showing here along the y-axis are the errors of taking a point from X and putting it on Y. And you can see that the larger the radius of the error of hitting a point in X into Y is the larger the radius of the ambiguity circle is. You can see that the correspondence is better, obviously. So the more you are close, it's like an ROC curve. The more you are close to 1, the better the matching is. So you can see that we are doing almost using unsupervised learning as the supervised one. In fact, you can do more than that. You can feed the same surface into this network and learn the features that the network should use in order to solve for the C function. So again, what we remember that in order to solve for the C function, we need a lot of corresponding features between surface S and surface Q. And the network is basically learning these features. It feeds into the network, for example, short or whatever features that you would like. And the network knows how to combine between these features in order to come up with a sequence of features that would allow us to solve very efficiently for C. What else can we show here? These are slides that Oshri sent me just yesterday. Let me see it here. So you can see that you can generalize. This is the Faust of people in motion. And we get better results compared to the most recent advances in this field by learning on a single cat and then generalizing. And there are some errors, but still it is better than other methods. It is also interesting that you can do matching by parts. I mean, you can train the network to overcome this kind of cuts. And remember, everything is working in the spectral domain. So up to a point, you can do matching. I mean, you more or less get the hang of where the face of the dog is. But obviously, you cannot expect to get really accurate results. And comparing, for example, to a new object, the network can learn the features from the object itself. So in a sense, it can self-train itself on a new object that it has seen. And if you compare it to, I don't know, a functional map net or just the functional map, then you can see that there are these kind of errors that the functional maps are introducing. And the learning mechanism obviously can take care of that. There is another slide in which Oshri was showing that if you're looking at the worst example of the supervised compared to the unsupervised, then the supervised wins by some epsilon. And if you take the worst error, then it would give better results. So in sense, these are two comparable results. I still have a couple of minutes, and let me use them cleverly. Try to. So let me tell you what the idea is right now. An interesting paper that three of my students did a couple of years ago is the following. They wanted to train a network to get an image and synthesize the geometry that corresponds to this image. For that, they resorted to now, we don't have a lot. If you would have had millions of couples of geometries and photometries of images and corresponding geometries, this would have been an easy task. I just feed it into a network, the network learned the relation, and everybody's happy. We didn't have that. So for that, we built a synthesizer. And the synthesizer was a result of what is known as 3DMM, or three-dimensional morphonormal model of Vetter and Bluntz. It's a linear model. And the linear model, these are the results of the linear model, creates images that looks like that. If you look at each and every object here, it would look like a person after a stroke. But still, you can use that in order to train a network. So you just randomize, and this is how the geometries are looking like. So this is an initial way of training a network, so we can do that. And now we can play with the pose, with the orientation, with the lighting condition, with the background, and we can feed all of this to a network. And the output should be Leonardo DiCaprio in a dimension that you have never been able to see before. Now, remember that we trained the network by guessing numbers from a linear space. So this would have been about 200 numbers that we learn, and then these 200 numbers hit by the corresponding eigen faces would give us the geometry and the photometry. So the first network that we trained, in fact, produced this nice looking face that you see over there, but all the details were gone. And then what we did is we injected back the shapeform shading because we have some rough estimation of the shape, and we have the photometry, how the image looks like. So you can just penalize for the discrepancy, and you inject back the 3D, the fine structure of the 3D. And the results were actually good. But then the question was, if the shapeform shading is an axiomatic model, why can't we train a network to do that? And this was the second idea. So again, the latent space is still the linear space of the 3DMM. And instead of just doing shapeform shading, we train the network to do the shapeform shading, and we still get nice results. And the final one, which I think is the most impressive one, and I will show you in a moment results, takes the 3DMM idea, for training, but does not go through a latent space. So there is a shape from shading penalty and the 3DMM result, and you can penalize in the middle, but it doesn't go through any intermediate space. In fact, there is a U-net that goes all the way. So the intermediate results looked like that, not bad, but still, and the final results look like that. Let me just go faster into some of the examples that we are really proud of. And you can see that the results that we are getting are quite good. In fact, the code for that is online. You can download it and you can test it. And let me tell you that we're still happy to see that these results are among the best they are, especially if you'd like to reconstruct fine features. Okay, so now 2 new students that I have. So this is Richardson and Sela, Matan Sela and Elad Richardson. Both of them, unfortunately, graduated. This is what happens to good students. And now I have 2 new students, which actually took it to the next level, and now they are training GAN, generative adversarial networks, that are able to reconstruct shapes, 3D geometries that looks like that. So they completely got rid of all these distortions that we have in a linear model. You can actually extract expressions, and you can extract faces that look like that. And then the question is, do we overfit? Okay, so Robin showed yesterday the problem of does the GAN actually overfit? And even more important is, do we actually mimic, in a sense, the distribution of faces in nature? So what we did for that is fed all these faces into an identification mechanism, and we measure the discrepancy between each face and each face, the original ones and the synthesized one. And then we come up with numerical as well as graphs like that, where here what you see, each and every yellow point is a real face, the distance between identities of a real face, and the red ones are the results of a GAN. And what you see over here is the results of the linear model. So in the linear model, since we are picking up from a Gaussian distribution, you can see that what you get at the end of the day is the Gaussian distribution. In that case, you can see the different ethnic groups, in a sense, and in fact, you can actually see genders within each ethnic group. So the GAN would capture, in a sense, the geometries of the space of all faces. And this is, using the NVIDIA training of the GAN in order to show our results, and we called it Guns and Roses. And I think this is more it. So thank you for your attention. Oh, and recently we have been, my daughter and I have been busy doing graffiti. So if anybody is visiting the Technion, you're welcome to our parking lot. And then you see the diagram of Hausdorff rocks. Thank you for your attention.
Question?
Thank you for your presentation. At the beginning of your talk, you mentioned curvature. There are many algorithms for computing curvature on contours. Which one do you use?
So for approximating curvature along a contour, what we use is Hume's method. There is a method, not Hume, sorry, that was developed in ancient Egypt of taking 3 corresponding points and just computing the radius of the, it's very easy to compute it. If you're talking about the curves, so you can just approximate it by, it's a very simple trigonometric equation. For surfaces, for example, you can take the Laplace-Beltrami operator and just apply it onto the coordinates of the surface, and you get the mean curvature vector. The mean curvature vector. Also in the normal direction. There are many ways to compute. Now, what I have shown you, the blue line that I have shown you, is in fact taking a sequence of points, the coordinates x, y of the points, and feeding it into a network. So you have a neural network that is trained to get a sequence of points ordered, and then the output would spit up a single scalar number that would now, How similar would this network be to this kind of approximation? I have no idea. Obviously, it takes much more than what we think of, because it would take quantization, and its goal would be to match between corresponding patches of surfaces. So this is more or less it.
Other questions?
So in this framework, how easy it is? I guess it is to introduce extra data on the surface, on the shape, like temperature or measurements.
So again, what you think is different features on the surface?
Yeah, that you have from some measurement, or you
No,
just.
well, I didn't tell you how we are actually computing these features. For the time being, they use SHOT. SHOT is this kind of histogram of orientations about each and every point. If you have a more clever feature, for example, a color, then just feed it into the network, and the network would learn, show the surface of the color at night or where it's cold, and you have a sequence of those, so the network would learn how to pack them together so that it would be easy to solve for this C function. So you can do whatever you like, but you need to obviously to train it somehow. You need this data to be accessible.
Any other question? No? Thank
Okay.
you again.
Thank you.